afternoon. Today I will present my project, which is a regularization study on the digits dataset using LENet5. The main goal of this project was to compare several common regularization techniques under the same training setup and see which one improves generalization the most. The key result is simple. All 5 regularization methods performed better than the baseline, and label smoothing achieved the best test accuracy at 99.26%. Now, the core question behind this project was, if I keep the dataset, model and optimizer, and the training budget fixed, which regularization technique gives the best improvement? I intentionally choose a moderate dataset model pair rather than a very large benchmark. The reason is that I want the comparison to be interpretable and easy to reproduce, while still showing real overfitting behavior. So the study is controlled. The only thing that changes from one experiment to another is the regularization method. The dataset is scikit-learn digit dataset. It contains 1,797 grayscale handwritten digit images across 10 classes. The original images are only 8 by 8, so I resized them to 32 by 32, converted them into tensors, and normalized them. The data split was stratified with 1,257 training images, 270 validation images, and 217 test images. For the model, I used the LENet5 adapted for one channel 32 by 32 input. I trained every experiment with ADAMW, learning rate 0.001, batch size 128, and 40 epochs. For fairness, I selected the best checkpoint using validation accuracy, then evaluate that checkpoint on the test set. I compared 6 total training configurations, 1 baseline and 5 regularization methods. The baseline has no extra regularization beyond standard normalization. Weight decay adds a penalty on large parameter values through the optimizer. Drop out randomly zeros classifier activations during training, which is meant to reduce co-adaptation. Label smoothing softens the one-hot target labels, so the model is less likely to become overly confident. Random erasing removes a random patch from the training image, which acts as data augmentation. Finally, mix-up blends pairs of samples and their labels, which encourages smoother decision boundaries. These methods intervene at different parts of training, so they are useful to compare side by side. And this slide shows the most important results in the project. The baseline reached 96.30% test accuracy. Every regularized model improved at that number. Label smoothing performed best with 99.26% test accuracy, which is a gain of 2.96 percentage points over the baseline. Mix-up was second with 97.78%. Weight decay and random erasing both reached 97.41%, and the dropout reached 97.04%. So the ranking is very clear. Label smoothing is first, mix-up is second, and the other 3 methods form a middle group. This result already suggests that on this task, target-side regularization is more effective than simply injecting noise into the network. Okay, this slide looks at how validation accuracy changed during training. The baseline learns quickly, but it plateaus relatively early. By around epoch 20, it is already close to its final level. Label smoothing behaves differently. It continues improving later into training and ends at the highest level. Mix-up starts more slowly, which is expected because it is training on interpreted examples rather than on clean images. But even though it starts slower, it keeps improving and catches up late. Random erasing also has a slower early phase, which makes sense because the augmented training images are harder. So this figure helps explain that the methods are not just changing final accuracy, they are also changing the shape of the learning process. Okay, now let's look at the generalization gap analysis. Here I compare the generalization gap, which I defined as clean training accuracy minus validation accuracy at the selected checkpoint. The baseline gap is 2.86 points, which shows mild overfitting. Label smoothing reduces the gap to 1.40 points, and the mix-up reduces it to 1.61 points. That is important because these are also the methods with the strongest test results. So on this project, smaller gaps usually matched better generalization. Weight decay is the interesting exception. Its gap is not the smallest, but the test accuracy still improves. That suggests it helps in a narrow way by making the final solution more stable, even if it doesn't reduce the gap as much as label smoothing or mix-up. My main interpretation is that target site regularization worked best for this dataset. Digits is a small handwritten digit dataset, and some examples are naturally ambiguous in that setting. It makes sense that reducing overconfidence helps more than simply making the network noisier. That is why label smoothing performed best. It directly prevents the model from treating every training label as an absolutely certain target. Mix-up also worked well for a similar reason. It smoothes the decision boundary by forcing the model to behave sensibly between examples. And weight decay gave a modest but reliable improvement with almost no change to the pipeline, so it is a good low-risk option. Dropout and random erasing helped too, but their gains were smaller. In this compact network, classifier noise and augmentation helped, but not as much as targeted smoothing. Okay, to conclude, the answer to my research question is that label smoothing was the best regularization method in this study. More broadly, the project shows that regularization matters even on a relatively small handwritten digit task. All the 5 regularized models outperformed the baseline, but the strongest improvement came from methods that controlled confidence more directly. There are also clear limitations. It only used one dataset split, one random seed, and one hyperparameter settings for each method. If I extend this work, the next step would be multi-seed experiments, confusion matrices, and calibration analysis. Thank you. In fact, this is all the content I present for you. Thank you.